All right, the last example, example 6. What is the maximum volume of a cylinder inscribed within a sphere of radius r? So, we can go ahead and consider a sphere. Something like that. And then if we build within this a cylinder, so something like that. Not my best drawing, but you get the idea. How big of a cylinder can we fit if the edges have to connect to the sphere or touch the inside surface of the sphere? That's what an inscribed cylinder is within a sphere. Okay, so one thing we can do here is imagine squashing this down into the page. And then really what we would receive here is we can sort of look at a two-dimensional version of this. So here I'm going to draw these within the xy plane. So there's the xy plane. And then if I treat this circle here as just the sphere being smushed into the page, then the cylinder gets smushed into a rectangle. In which case, the radius of our cylinder and our height need to be figured out relative to over here. So we know that this circle, right, if we're just taking this sphere of radius r, and if we smush it into the page, then this means our circle has radius r as well. The equation of a circle of radius r, centered at the origin, is x squared plus y squared equals r. Something that you'll get a lot of practice of in Calc 2, but part of it starts now, is knowing that if you have something connect to the graph of something, so for instance this point here, we can say that this point is just a point x comma y because this point satisfies the equation of the sphere. So since we're just considering these points as kind of being anywhere, right, we could have made our cylinder longer and skinnier. This is just some arbitrary point on the graph of this. So we can treat this point here as an x comma y pair that satisfies this equation. So if this is an x value of x, then that means this distance right here is x. So that means the radius of our cylinder is just x, and the height of our cylinder, well, height is this distance doubled. So 2 times this distance. Well, since it's attached to this point, that means this has to be a value of y. So the height would be 2y. So now let's think about the volume of a cylinder. The volume of a cylinder is pi r squared times the height, but because we know that the radius is x and the height is 2y, we can replace this to get 2 pi x squared y. And now we have a function of 2 variables. But we also know that the points have to satisfy this equation. So we could rearrange and solve for one of these so that we can make a replacement into here. Now you could solve for y up there, but then that would force you to take a square root. Instead, we could just solve for x squared, right? X squared plus y squared equals capital R squared. This is no different than x squared equals capital R squared minus y squared. And then we create a function of the variable y, which is equal to 2 pi x squared times, x squared is being replaced by r squared minus y squared times y. So that becomes the volume of that cylinder inscribed within a sphere of radius r, where half the height is y. Okay. So now we have to think about how big what's the domain for y? So what's the smallest y could be? Well, the smallest that y can be, right, up here, y is r, but then over here we get y is 0. So 0 is going to be that. And then what's the biggest y can be? The biggest y can be is r. Okay. So with that, we're free and ready to take our derivative to find critical points. So the derivative here, upon simplification, should be equal to 2 pi times the quantity r squared minus 3y squared. Again, there's some simplifications that I'm not showing here. This is continuous, so we don't have to worry about the derivative not existing. We only need to worry and check where the derivative equals 0. If you do this and solve, you'll get y equals plus or minus r over the square root of 3. But again, that's not in our domain. Y is not going to be a negative value, so this is going to be, we're going to just keep the positive value. So now we can compare our values. V of 0, V of r, and V of r over the cube root of 3. When you plug in 0 and r, you get 0. And when you plug in r over square root of 3 and simplify, you get 4 pi over 3 root 3 r cubed, which is clearly the maximum. And this question asks us, what is the maximum volume? So they only wanted to know what this number is, so that's the end of the problem.